Well, you can probably judge by the fact that I'm wearing a cap that the experiment was a failure. When I came to look at the fourth session of this board to see, well, firstly it just wasn't there, and there's a message on the camera saying insufficient light, so it just failed. So I've now had to switch on the light, and hence my cap, and I'll just record it again, which is what I'm doing. But this time, you know, you'd think after, I've been doing this, what, 4 months now, this whole deGarisMPC thing, 4 months, I think that's right. And you'd think that things would have settled, you know, that I've found some modus operandi, some, you know, approach that would work, in which all problems are solved. But no, it's still going on. So this time I put a paper, like thick paper cap. Like here's the lamp that's causing me the trouble, and there's a modern type bulb, low energy, but the light coming from it is very concentrated, so it's a very sharp light. So what I've done, and I've got a sort of glass cover around it. So what I've done is made a kind of paper cap, and I've put it at the bottom here, so it blocks the light coming straight down. So if I look up, I don't see it so much, so it's not so bad. And the reflection of the light on the whiteboard to my eyes, that's now made a lot less, so that may help. Another thing I can try, just constantly trying things, I may pressure myself more to be finished before the light gives out, but it's now late September, so you know, as I get more and more into winter, there's going to be less and less light, so I'm going to have to bite the bullet and just buy a different lighting system up there, you know, with a proper light, with diffuse light, not sharp, concentrated light, which I suspect is burning my retina. And I have to be careful, right? My eyes are precious to somebody like me. All right. Okay. So we're talking about the application of regular expressions to compilers. And so, let's see, try and get back into the swing of things. Now, inside a compiler is something called a lexical analyzer. Lexic, just sort of like letters. So it's a piece of software, part of the compiler. It looks at regular expressions and then translates those into software that then can be used to detect tokens in the user's software code that are described by the regular expression. So now it doesn't really matter if you don't, if you're not a computer guy at all, don't worry, because all this is just an example of regular expressions being used. A major application of regular expressions in computer science is in compilers. Right, so let's move on. Now, major new topic, and I'll try to justify it, make it plausible to start with, and that is finite automata and regular expressions. They're equivalent, and that may seem a bit surprising because they seem, you know, two totally different things. I'll try to make it plausible that they are equivalent. A finite automaton, what's it doing? Well, it's recognizing a language. Okay? So in other words, it's accepting all the strings in that language. And it's the word language that's the critical thing. That's what's in common between the two. That's what creates the equivalence between the two. Now, a regular expression, what's that? Well, it's a description of a language, ultimately. How do you make a regular expression? Well, you take regular languages and you operate on them with regular operators like union, concatenation, star, okay? And the result is another language. Okay, so that regular expression you can evaluate, and you'll end up with a language, a set of strings. Now, if that set of strings is recognized by a finite automaton, an FA, then intuitively you sort of think, well, isn't then the regular expression that generates or describes that language, which then is recognized by that automaton, then wouldn't that mean that somehow the regular expression and the finite automaton are equivalent in some way? Because they both operate, describe or recognize the same language. Okay, so that's why the two. It seems plausible that the two are equivalent. Okay. So let's see. Well, in formal terms, well, before we get onto a theorem, but so any regular expression can be converted into an FA. Okay, well that's a major idea. You can take a regular expression and convert it into a machine, into a finite automaton. Okay, and that finite automaton recognizes that language that the regular expression describes. Okay, so you have a language. On the one hand, the regular expression describes it. On the other hand, you have a finite automaton that recognizes it. Now, if from the regular expression you can convert, build, create a finite automaton that recognizes that language that the finite expression describes, then the finite automaton and the regular expression are equivalent. That's sort of the idea. Okay, now we express this more formally. Oh, by the way, a bit of a reminder, a regular language, by definition, is a language that's recognized by some automaton, some FA, finite automaton. Okay, that's a bit of a reminder. Okay, now a theorem, we'll make this more explicit. So it's theorem 1.54. And here's the theorem statement. A language is regular if and only if some regular expression describes it. Okay? Now it's an if and only if, so we have to, to prove this theorem, we have to prove it both ways. So I've helped a bit by isolating which is the P and which is the Q. So it's an if and only if proof, so we can simplify it to like P, IFF, P if and only if Q. So what's P? P is the mathematical statement that a language is regular. The language is regular. And Q is the mathematical statement. Some regular expression describes it. What is it? Well, it's the language. It refers to the language. Okay? So we have to show if P then Q, and we also have to show if Q then P, because it's an if and only if type proof. Okay? We've talked at length about that before. So we can describe this in terms of arrows, P double arrow Q, or in terms of letters, P, IFF, if and only if Q, right? Okay, now Sipser, he, I don't need the hat, do I? I'm not sure, in this direction. Okay. It never stops.